Okay, welcome everyone to this continuation of what are my favorite theorems, my very biased collection of my favorite algorithms. So today I would like to talk about one of my favorite algorithms, or a flavor of one of my favorite algorithms. We'll see that at the very end. But the problem I want to focus on actually comes from geometry. Maybe not quite just from geometry, but it kind of has a lot of real world applications. So it's very popular in machine learning, for example. It's this nearest neighbor problem that we will see, yeah, throughout this video. And yeah, whatever it is, it will be something like closest friend problem. But let's get started with some real world application. So whenever you write a document, there will be some spell checker involved, and I'm really thinking about the old school spell checkers that I've used in my life, not the the new type of spell checkers. So I really just want to have this idea. I just have some word like this one here, and yeah, I try to find the closest approximation of that word. It doesn't appear in my database, so what is it? And this is a spell checker. The more fancy versions that everyone hopefully uses nowadays also can make sense of a little bit of context. So here, except is spelled completely correctly, but the correct word here to use what would be expect. So I'm not going to cover that. You need some slightly different ideas to do that one. I will try to stay with this one. So more the classical version of spell checking. And essentially it works as follows. Obviously I'm oversimplifying things because that's what mathematics is all about. And it's what YouTube videos should be all about as well. Kind of don't make it too complicated, just oversimplify things at the cost of losing a bit of precision. That's totally fine. But anyway, roughly it should work as follows. We have a set of words, our database of words, something, hanging around here in some high dimensional space, R to the very large N, where N is roughly this kind of dimension. You have different dimensions for different types of words. So whatever, how tall, whether a word represents a tall thing, then you have a tower or a building or whatever, whether it represents X, Y, Z. So you have very many dimensions for potential words, and you have the zoo of words in your database. And then the user types in a new word and ends up somewhere not in the database. And what the spell checker kind of suggests is kind of the word that is closest to it in some form of distance, right? So the closest neighboring point. And then, as you can see in the spell checker, potentially also the closest neighboring points. Now, this is roughly what a spell checker is. The collection of words in a high dimensional space where the dimensions kind of correspond to meaning of the word, and you put in a new word which is misspelled, so it ends up somewhere in space but not on one of the data cluster points already. And yeah, so whenever that happens, you just want to find the kind of the closest one, and that's what the spell checker should actually do for you. And the geometric formulation is really just you have a bunch of points as here in let's say in the plane in this case, so squared, whatever, and we are looking for the pair that's closest to one another. Let's say those two in this case. So we're looking for the distance between the two, and really what closest means is just depends on the context. So you can vary this by running this in any metric space. Really depends what closest really is, but let's just say with a standard one here, R2 and geometric. R2 and the Euclidean distance, the usual distance between points. And we want to find the closest pair of points. And we want to do that efficiently because, as I said, this is kind of a real world problem. So a lot of real world problems you run on a computer will do some form of this algorithm. So we want it to be kind of as fast as possible because it will run like a million times, right? Well, maybe that makes some sense. It will run a million times, so we want it to be fast. And if you do it in a naive way, then it actually runs in O of n squared. So O is just notation for the worst case scenario. So in the worst case, n is the number of points. So n is number of points and the worst case scenario here would be n squared. And why is that? Well, let's do the worst case scenario. So let's say we want to figure out as a naive approach. Let's say we want to figure out the closest distance Maybe these are a little bit too many points. Let's just say we have 4 points and we want to figure out the closest distance. So what do you do? You would start with some point, measure 3 distances to the other point, points. Take the next point, measure 2 distances. Take the next point, measure 1 distance. So you would get something like 3 plus 2 plus 1. What was my color here? Orange. So you would have 6 different things you need to check. And if you remember how the formula looks like for the sum of, well, you do that for n points, so the sum 1 plus 2 plus 3 plus 4 plus 5, then it is roughly n squared. So the naive algorithm will run in roughly n squared time. And yeah, so that's not very exciting. N squared is not bad, it's not good either. And it turns out that it can do much better than this. And I'm going to explain a much better algorithm. But before, let me state I think current state of the arts is the fastest non-random algorithm runs in this time. The fastest random algorithm that runs in linear time, so O of n, which is like really fast. But for randomized algorithms, you usually pay a price. Like you only get the correct result in 99.99% of all the cases. So let's focus on the one which is n log n, which is essentially linear because the log doesn't move at all. So here I plotted them compared to one another. This is the n squared one, the naive one, and there will be one that I'm going to show you. The n log n is here, and then the n and n log n, you essentially can't distinguish them anymore. So n log n is a little bit faster, just a really tiny bit faster than linear. Yeah, so I call this essentially linear. Okay, that's pretty good. It's just really much faster than n squared. And as I said, this is just so applicable in real life that it's just really important to have it very fast. I should give you here, so that was a bait, I should give you the catch as well. First of all, we have fixed the dimension. So you could think about this problem as varying the dimension, and there will be a scalar, right? So the O notation kind of suppresses scalars, so we have some scalar in front. There will be a scalar depending on the dimension, and this scalar is usually terrible, at least for some of the algorithms. So be careful a little bit. So I think if you usually try to, in this case, for example, if you would like to have the problem in the number of points in the dimension, then it's less nice. It's very far away from linear actually. So this is one catch. The other catch is a little bit that is, very classical to analyze algorithms by an upper bound. This is what this the big O notation does. But it is actually maybe not the right thing to do. So what you usually should think of as is an analysis of the average runtime. I don't know many algorithms which are actually analyzed for an average runtime. I haven't seen anything for this one in particular. But that's roughly really what you want to do in practice, right? If you run this in practice and it runs very fast on 99.9999% of all cases, then this is good. And even if there is a 0. Whatever it was percent of all cases where it's really slow, so the n will, or the upper bound will be really large, but the algorithm is still good. So this kind of this analysis of the average runtime is a little bit lacking in the field, and it's really just because it's much easier to get an upper bound than to get an analysis of an average runtime. Anyway, the upper bound here is essentially linear, and I wanted to show you how to get it, but I find this algorithm a little bit complicated, so I decided to go for the algorithm, or an n algorithm that gives this runtime here, and it works as follows. It's kind of a cool problem. It's called divide and conquer, not divide and conquer, just divide and conquer. So divide and conquer, divide et impera. So you divide your problem into smaller pieces. You save a little bit during some process of merging them, and then you conquer by running it recursively. And this is how you do it. So you divide your problem set into 2 bits. Yeah, the left, let's say left and right here. And you just run the algorithm on left and right, and you will find, for example, this little pair down here in the right set, and maybe this little pair up here in the left set. And then you would need to analyze the merging. And in the merging process, you will save some time. And this is where the brilliance now comes in. And then you run it recursively. Because in the merging process, you don't need to compare, for example, this distance anymore. You don't need to know that, because this distance will be definitely bigger than the one you already calculated. No, what you only need to do is you only need to consider the smaller one. Let's say D1 is smaller. And then you only need to consider points in this little region around the cut. And this saves you a lot of time. And this is where you save time. And this is where the runtime kind of drops down from n squared to n log n. And yeah, so this is usually this idea of divide and conquer. So divide your problem into two sets. I run the algorithm on those two sets. It's usually much faster. And hope in the merging process you save some time. And here you do, because, well, you don't need to compare the long distances anymore. Anyway, I hope you enjoyed this video, and I also hope to see you next time.